All right. Well, excuse me. Good morning, and please check all the information on the screen. So, just a reminder about the homework. And this is the last slide we saw yesterday, 2 days ago. And this slide demonstrates how to calculate the magnitude of a new physical quantity we call the electric field strength, or shortly E field. And it depends on, for a single point charge, it depends on the magnitude of the charge and on the distance from the charge which generates that field to the location where that field is being measured or calculated. So we have to keep in mind the difference between a charge which generates electric field, we call it a source, and the charge, how the sound? I cannot hear myself. Okay, thanks. And the charge which measures the presence, the strength of the electric field, we call it the test charge. A definition of electric field is based on the force acting on a test charge. But this electric field has to be created, has to be generated by other charges, and those charges we call source charges. Sometimes we know, sometimes we don't know anything about the source charges. It doesn't matter. So this is how we calculate electric field strength if only one source charge exists and creates it. And of course, because a force is a vector, and a vector divided by a number is a vector, electric field also is a vector, which means it has a magnitude, and the equation is for the magnitude, and also it has a direction. And when we talk about direction, we have to use some other means, like pictures. So the question, what I want to ask you right now, what do you think about the direction of the electric field generated by this charge at this point? What you're all doing right now, and people call it thinking, is absolutely wrong. Physics doesn't require thinking, very rare. You have to use your hand to start drawing a picture, and that doesn't require thinking. It requires acting. You have to draw a picture, copy. Now you have to choose, what do you want to use? Do you want to use an expression for the magnitude of the electric field, or do you want to use something else? And for now, we only have two options, two equations. Number one is on the screen. Number two is a definition of the electric field, a definition which we used to introduce that physical quantity. So, if the question is about electric field generated by a charge, writing V equals V initial plus A times T doesn't make any sense. So what makes sense is starting using equations which have any relationship with electric field, and we have only two. Number one and number two is a definition. So you have to choose and then you have to use. And there is a hint here. A hint. So I'm going to give you last chance to look at the numbering. So because when you need to make your choice, you have to enter a number. And numbering goes, how do we call this direction? This direction. Clockwise from the vertical, 1, 2, 3, 4, 5, 6, 7, 8. So if you choose your number, you can enter it already. If you're still thinking about it, you know how to choose it. And here, the equation for the magnitude, which is correct, also useless, because the question is about direction. And if this equation is useless and we only have two, there's only one choice left: the definition, which relates a force acting on the test charge placed at that location where we are measuring the electric field. So you have to now use the definition. And to do that, you have to place, well, using your imagination, a test charge of your choice at the location where you measure or study electric field. Then look at the force acting on that test charge from this one, draw it, and then make a choice. What answer should you choose from the arrows on the screen? That's it. So right now, everyone has to have a test charge placed at the location where we're measuring electric field. And a test charge, this dot represents the location. So now you have to draw your own dot, which represents the charge, and you choose it. What would you choose? What test charge would be the easiest choice? One. And now you have to draw a force acting from the source charge on the test charge. That's an arrow. And that arrow doesn't have arbitrary direction, because when we have two charges, they only repel or attract each other. So, right? Let's see. Today, some very, very smart person used a huge truck driving under the bridge on the Store Drive and blocked it. So for me, it took extra 40 minutes, and I assume maybe people still on the road. So that's probably is the reason why we have only 51 students out of 67. I hope that's the reason. And now we have a distribution. And that distribution tells us the correct answer is 8. Because if we place a test charge, doesn't have to be one, just positive is sufficient. These two charges will repel each other. And what does it mean, repel? Can a force acting on the test charge point like this? No. Wrong. Because repulsion should be happening along the line connecting these two charges. That's what repulsion means. So this force has to point away. That's the force acting on the test charge. But as we know, if the test charge is positive, hence electric field and the force parallel to each other, which means electric field also should point away from the source charge. That's it. That's the reasoning. And of course, if we choose any other location, let's say here, the exactly same reasoning would tell us that electric field at that location should point along this line away from the source charge. And actually, if we move closer here, electric field still will point away from the charge, but it will be stronger. And if we move away along the same line, electric field still will point away, but will be weaker. The magnitude of the electric field of a point source charge decreases according to the equation with the distance. Well, okay, what we have now is the answer, and now it's not a question, but we can repeat exactly the same reasoning for a negative test charge. So if we place a negative source charge, if we place a positive test charge at the location around the negative source charge, it will be attracted. So that's the test charge, that's the source charge. The test charge will be attracted toward the source charge. That will be the direction of a force. Now, this equation, which relates electric field, force, and charge. What kind of a charge do we use in this definition of electric field? The source one or the test one? The test. So, even if the source charge is negative, the test charge is still positive, which means still electric field and the force acting on the test charge parallel to each other. So electric field must have the same direction as the force acting on the positive test charge. And now it means toward the source charge. And of course, we can go to a different location, let's say here. Same reasoning tells us that if we place a positive test charge here and measure force, it will point toward the source charge. That's going to be electric field. And the closer we are, the stronger the field is. That's the answer for this particular situation. And now this slide represents the summary. How do we calculate the magnitude of electric field? And the equation doesn't depend on the polarity because it uses the absolute value of the charge. But the direction of electric field depends on the source charge. Electric field points away from positive charge, and electric field points toward the negative charge. Now, what do we do if we have several source charges? We use the same idea we used for forces. When several forces act, we need to calculate net force, which is, according to a definition, just the sum of each individual vector force. Now, we can place a test charge, number one, measure force, and that force will be equal to the field if it's 1 Coulomb test charge. So exactly the same relationship now we can write for the net electric field, for the total electric field. If we have several set of charges, each individual charge generates its own electric field, and the net total electric field has to be equal to the sum of each individual fields. That's it. We call it a superposition principle. Superposition means sum. That's it, nothing else. The principle of the summation. And question now to you. We have two charges. One is positive, one is negative. Can we calculate the total electric field generated by both charges together at the given location? So I'm going to give you 30 more seconds to choose your answer. And the survey says there was no answer number 4 present on the screen. So at this time, I assume it's an honest mistake. Yes, we can, because we know how to calculate the individual electric field, and we know that the net field has to be equal to the sum. So let's do it very quickly, because mathematically, this problem is no different at all from calculating net force. And first, we have to draw a vector which represents the field generated by one charge. And that field vector should point away from a positive charge. And we call it E1. And we call this charge number 1, and we call this charge number 2. Now we need to draw a vector which represents electric field generated by the negative charge, and that's supposed to be directed toward the negative charge, and we call it E2. Well, strictly speaking, until we finish calculation, we don't know the direction of the net electric field. So we don't care. We have to finish calculation, and whatever happens, happens. There is no sense to think about it. So next step is calculating individual electric field. So we can calculate the magnitude of the first electric field. We used exactly the same equation for the magnitude of electric field of a point charge for both fields, but we use it twice. First time, we have to use, well, same constant, and the charge of the first charge, and the distance from the charge to the location where we are calculating field. And that will be 7 meters, and we have to square it. And the unit will be a Newton over a Coulomb. Now, we need to write an expression for the magnitude of this, yes?
Sorry, which charge are we using? The 9?
This is,
Sorry, yeah.
this is a 9.
Yeah, sorry. Is it referring to the red sphere? Charge that we're using?
Yes. This is, you see number 1. That's Q1. That's Q2. And my Q and my 9 look alike. So that's why I read it. And the charge is nanocoulomb, so -9. And for the second individual field, we have to write the same constant. What should I write for the number which represents the charge? 4 Do you see two vertical bars? They make everything positive. So 4 times 10 to the negative 9 divided by, now that's supposed to be distance from this charge to the same location, which is 4 meters squared. Done. Well, we can, a Newton over a Coulomb. We can simplify, right? So what can we do? Here and there. We can cancel these factors, which is a good thing. And now we have 81 over, what is it? 63, 49. Yeah, I want a 9. There's no 9 here. I can't cancel it. Why can't I cancel? Oh, I said 49. 70. And here I can cancel something. That's a good thing. So 9 over 4. That's it. Now we have to calculate the x component of the net electric field. So we introduce the x-axis, and the x component of the net electric field will be equal to the magnitude of E1 minus the magnitude of E2, which will be equal to 81 over 49 minus 9 over 4. Someone has to calculate it. And tell me the answer. So 2 things I recommend to do every day when you do a homework, using your own calculator always to get familiar with it, and print out the equation sheet and use it every time when you need to find an equation, so you would also get familiar with it. So the answer is negative. And negative sign means the net field actually points to the left. Even if the positive charge is stronger, but it's farther away, right? So. Well, now, yes?
Sorry, are we subtracting E2 from E1 because E2 is a negative value? Like
E2 is a vector, and that vector points to the left, opposite to positive x direction, and every vector which points opposite to positive direction of the axis has a negative component relative to this axis. So technically, I have missed one step. I made it in my mind, but I can try to fit it. The x component of the net electric field should be equal to the sum of the x component of the first electric field and the x component of the second electric field. When we do components, we're just adding components, but each component, because it is a number, may be positive, may be negative, may be 0. And the first component is positive and the second is negative. That's a part of the vector analysis. So we answered practically the same question for the location of the net force. Yeah? But exactly the same reasoning, we can repeat for a location where net field will be 0. First, we can imagine that we just placed 1 Coulomb positive charge and it has no force, so nothing different. But as an exercise, we can also draw arrows which represent electric field. And when we draw arrows, vectors which represent electric field of one charge, we completely forget, ignoring the presence of the second charge. So at first there is only charge, positive charge, and when we are very close to it, electric field is strong and it must point away from it. Away means away. When we are to the right to the positive charge, away means to the right. When we are to the left of the positive charge, away means to the left. And when we move in further away from it, electric field decreases. That's it. These red arrows represent electric field vectors of electric field generated by the positive charge. Now, negative charge generates electric field directed toward it. What does it mean, toward? Well, that depends on the location. If we are to the right to the charge, the direction toward means to the left. If we are to the left to the charge, the direction toward means to the right. And when we move in away from the charge, electric field decreases in magnitude. So, net electric field is equal to the sum of electric field from a positive charge and electric field from a negative charge. And we can see that net electric field to the left to the positive charge is never zero. It is not as strong as electric field of a positive charge, but still it's never zero. Between the charges, electric field actually is very strong. We are adding red and blue arrows. And so what's left is, well, this region. Technically, we don't really have to do all this. We can just guess a location and calculate the distance, and that's it. The number will tell us everything. If we do it accurately, if we calculate not distance, but x-coordinate of that point, it might be positive, might be negative. Let's do it very quickly. So, again, that's the x-axis. Let's set it to 0. This is some distance. I think somewhere else we will know that distance. Q1 equals 3 times, and this Q represents some fixed value. Doesn't really know what value does it represent, but it is a fixed value. So our assumption is somewhere here, electric field, net electric field will be equal to 0, which means here electric field from a positive charge will be canceling out electric field from a negative charge, and we write them E1 and E2. And since they cancel out each other, the magnitude has to be the same. Hence, well, what are we looking for? Let's say we are looking for this whole thing, which we call x. K times 3q over x squared. This expression represents the magnitude of the electric field strength due to the first charge. And it has to be equal to the magnitude due to the second charge. The magnitude of a negative q is just a q. Now, you have to keep in mind this is the distance from the charge to the point, and that distance is not x, that distance is not d, that distance is x minus d, and we have to square it. That's it. We have solved this equation before. So if we cancel q, if we cancel k, and if we take a square root of everything, what's left? Square root of 3 over x should be, well, technically, we're assuming it's positive. Technically, it should have been magnitude of x minus d. And you can solve it, calculate that x. So that's the picture. And now we have a distance. And now we have an equation with this distance, square root of 3 over x equals 1 over x minus 4, and I keep centimeters. So my answer will be in centimeters. Square root of 3 times x minus 4 times square root of 3 should be equal to x. X, well, square root of 3 plus x equals 4 times square root of 3. And x will be equal to 4 times square root of 3 divided by square root of 3 plus 1. Right? Oh, minus. Why didn't you say anything? That's a minus. That's a minus. Why should it be a minus? Because x should be greater than 4. We see it from the picture. And a plus would give a number less than 4, which is also a hint we made a mistake somewhere. All right, I've got the slides, the answer, question. These arrows represent electric fields, yeah? That's the individual electric field generated by that charge or set of charges. This is the individual electric field generated by another. That's a net electric field. To calculate the net electric field, first, the tail to a head rule was used. Another question to you, can you say something about the polarity of the source charges? So now we have to say something about the polarity of the source charges. Of course, you can discuss it with you. I'm going to give you an extra minute to do that. And your choice basically between two words, away or towards. That's it. Now, this specific slide gives you a simplified version of the question. An actual version would look like this. You have two sets of charges, and you have only one arrow, which represents the net electric field. That's it. So you would have to use the superposition principle backwards. You know that the net electric field should be equal to the sum of the field number 1 and the field number 2. So your goal would be draw those arrows first. And well, how do you do that? Well, you use the oldest scientific method, guessing. You guess. Well, the fancy word for that, you hypothesis. Yeah. So you guess, okay, let's say my vector E1 points like this, and vector E2 points like this. Why not? Good guess as any. Now, what you're doing? All right, I know the tail to a head rule, so if I use the vector addition, this arrow should represent my net electric field. Now I use my ability to compare things. Does this blue arrow look like the red arrow? No. So, wrong. That was a wrong guess. So we're moving on to the next one, to the next one, until finally we get the right guess. Well, let's call them again number 1 and number 2. These two arrows will represent individual electric fields. And now we start asking the original question, okay, if I have a charge, an electric field points away from it, what kind of a charge is that? Positive. We have it proved. If I have a charge, an electric field points away from it, what kind of a charge is that? Again, positive. So they must be both positive. We just have it proved. And I had a slide for that. Okay. Now we have to calculate the net electric field. And when we have to solve a problem, the first thing our brain has to do, we have to force it in doing that, is to search for something similar we've done in the past. And we have done it in the past. If you check the slides, lecture 2 slides, you would find a very similar picture. And every time when we find a similar problem have solved before, we just have to try to apply the same type of reasoning. So this is what we've done already. I didn't finish it in the class. I advised you to finish it at home. I don't know if you did your homework, but I did mine. Now, lecture 2 slides have solutions to all questions which were not finished in the class, including this one. In particular, the net force acting on the third charge in that problem has been found. It is actually equal to 40 nanonewtons. And now, if we know the net force acting on a charge, we can just apply a definition of electric field. Right here, there is a force acting on the charge of 2 nanocoulombs. Electric field is related to that force and that charge. The force is the result of a combination of the property of a charge and the property of a space where that charge is placed. An electric field is the property of a space. So basically, when we're calculating electric field, we take a force and we're trying to extract anything related to the charge. Extract mathematically means either subtraction or division. We cannot subtract variables with different units, so that's why we used the fraction bar for defining electric field force over charge. So if we use a magnitude, that's what we're looking for. That's going to be 40 nanonewtons divided by 2 nanocoulombs, so 20 a newton over a coulomb. But of course, we also have to be able to calculate the net electric field using just superposition principle. So what do we have to do for that? Well, each charge generates its own electric field. Here, well, again, we should call them number 1 and number 2. This arrow represents electric field generated by the positive charge at the location where we measure it. And this arrow represents electric field due to the negative charge. Now we have to add them up together. So this arrow plus this arrow. And I don't know technically yet how long each arrow is. I have to calculate magnitudes, and I will very soon. Together provide the arrow for the net electric field. And we know that the angle between the arrows is 90 degrees. So again, that's just a right angle triangle. So net electric field should have magnitude equals to square root of the sum of the squares. Now, it's time to use an expression for each individual electric field. K Q1 over R1 squared plus K Q2 over R2 squared. Well, K, now I'm doing some mathematics in my mind. That means I can make a mistake, so you have to check. K is the common factor. It's squared and taken square root of that. So what's left inside? Now I start using numbers. Q1, 9 nanocoulombs squared. Distance number 1, R1. We did that calculation before. It should be equal to the hypotenuse, which is 3, times cosine of 30, which is square root over 2. 3 times square root of 3 over 2 squared, plus K is outside. Second charge, 4 times 10 to the negative 9. I said 9, I wrote 6, I don't know why. Negative 9 divided by, that's distance from the second charge to the same location. And again, it has to be equal to the hypotenuse times the sine of 30, which is 1/2. And we have to square it. So this is 9 times 10 to the negative 9th. What do I see here? The same. 3 and 3. Common factor. Squared and then square rooted. So over 3. 1/2 and 1/2. Squared and square rooted. 1/2. 10 to the negative 9, 10 to the negative 9. Squared and square rooted. 10 to the negative 9. What's left inside? 9 squared over square root of 3 squared plus 4 squared. So how can we make it simpler? Positive 9, negative 9 getting cancelled. 9 over 3 is 3, and divided by 1/2 is 2. Inside we have an that's 9 squared over 3. 9 squared over 3. Am I missing anything? Can I make it simpler? Checking one more time. So constant. 9 coulombs. Ah, of course. Yes, absolutely. Thank you. So it has to be squared twice. By the way, it's a very, very common mistake, especially in the morning. So, 20 newtons over a coulomb. I just finished the whole calculation in my mind. And if you don't trust me, you have to do it on your own. And now, everything related to this part of homework has been covered in great details. So, moving on. First, we have to talk about a new visual representation of electric field. We've been using electric field vectors, heavily using. So if we have a charge, it generates electric field. To demonstrate the presence of that electric field around it, we used an arrow which points away from a positive charge and, oops, wrong magnitude, getting shorter when we move away from a charge. But if we have many, many different locations with arrows to draw, it just takes too much time. So instead, we just draw a line which represents the presence of all possible arrows in that direction. And this line has a name, electric field line. So if we have a positive charge, to represent the presence of electric field it generates, we can use lines. All those lines, straight, they point away from the charge, and they demonstrate a direction of electric field where? Anywhere. For example, here, electric field vector should point like the line does, but just have to be a vector. And an official definition of electric field line is just a line to which electric field vector is tangent everywhere to it. That's it. Now, for negative charge, we can repeat exactly the same reasoning. For the negative charge, electric field vectors point toward it. Well, strong, not as strong anymore. Again, strong, not as strong. But again, we can just draw a single line which represents the presence of all those vectors. And how do we point it? Toward the charge. So electric field lines which represent the existence of electric field generated by a negative charge, also, those are lines, they are infinitely long, but they point toward a negative charge. So now we have two different representations for the electric field. A vector, which we use to demonstrate electric field at the specific location, and lines, which we use to demonstrate the presence of electric field in general, everywhere. Now, let's practice. Let's say we have a dipole. A dipole is a system of two charges which have the same magnitude but opposite polarity. Of course, yes. Opposite polarity. One is positive, second is negative. That's what we call dipole. A dipole. If plus and plus or minus and minus, we don't call it a dipole. We just don't call it anything. So how do we draw a vector? Well, to draw a vector, we have to use a superposition principle. So let's say we take this point P. At this point, we can draw two arrows. One represents electric field from a positive charge. Second represents electric field from a negative charge. And now we can draw the net electric field. And we can repeat the same reasoning again and again on this line. And we get electric field line between the charges directed from plus to minus. Now what can we do? We can choose any other location. Here, we have to draw electric field vector, which represents electric field due to a positive charge. Now we have to draw electric field vector which points toward the negative charge, but should be shorter because the location is farther from a negative charge. Now we can draw the net electric field. We just need to add these two vectors. And now we have to repeat the same reasoning at several different points here, for example. Oops, I want it red. And now we have to connect. Well, we probably have to do it here. So now we're going to have a strong electric field due to the negative charge and a very weak electric field due to the positive charge. So the net electric field points like this. And now we have to draw a line which touches all those arrows. Yeah. Tangential means touching. And that line should look like this, something like that. It begins on a positive charge, and it ends on a negative charge, and we can repeat these reasonings again and again and again and again and again. That will give us a sense of electric field around a dipole. And if we repeat these exercises again and again and again, we always arrive at the same three properties of electric field lines. First, they never cross. Second, they always begin on a positive charge or at infinity. Yeah. They always end on a negative charge or at infinity. And we can use these pictures to represent electric field of any system, and we can use these pictures backwards. For example, now we can ask a question. If I place a negative charge here at point P, what will be the direction of a force acting on it? Well, I know what to do. This line tells me that at the location of point P, net electric field should point, well, like this. It should be tangent to this line. That's the net electric field. And if I want to calculate force acting on that charge, I have to multiply two numbers, charge and field. Well, a number and a vector, sorry. And if a vector has a known direction, but the charge is negative, that means force must point opposite to field. This arrow now represents the force which will act on a negative charge placed here. That's it. That is, bless you. That is why electric field lines are convenient. If we know how to draw them, we can figure out a lot of information about forces acting on charges. Now, the equation for electric field strength and the equation for force of gravity are similar. So there is a deep similarity between gravity and electricity. And well, see, this is the Newton's law for gravity, and we apply it for a very large object when we're very far away from them. If we're getting closer and closer and closer, turns out the same force can be found using much easier equation. It's the same force. Why is it possible? Because when we are very close to a surface of a large number, all those arrows now have practically the same direction. And if it's the same direction, we call it a uniform field. So if a uniform gravitational field gives a force which is equal to mass, which is gravitational charge, times gravity, which is gravitational field, we can make an assumption that for a uniform electric field, we get a similar result. And yes, we do. First of all, how would we generate a uniform electric field? We would have to have a very large, flat, charged surface, nothing else. So if this table would have been made of plastic and uniformly charged, we could have a test charge moved left and right close to it, and the force acting on it would have been the same, uniform. And the force over charge, that's what the field is. And the expression for calculating the strength of the uniform electric field generated by a large charged surface is this. It only depends on two variables: the total charge of this surface and the area of this surface. Basically, it's a charge density. That's the meaning of electric field, close to a large charged surface. And also it has a constant, a fixed number, 8.85 times 10 to the negative 12. We don't have to remember it. It's on the equation sheet. We don't use it very often, but still. Well, so an exercise for us. How would electric field between two charged plates look like? It's not a dipole. Yeah. Both plates have exactly the same magnitude. Both plates have the charge with exactly the same magnitude and opposite polarity. But we cannot call it a dipole, because for the dipole, we would have to have 2 point charges, no size. Those should be imagined as very large, theoretically infinitely large flat surfaces with exactly equal but opposite charge in it. So well, of course, we have to start from one plate first. So let's imagine this is a very, very large, positively charged plate. And the charge is spaced uniformly, so density of the charge is constant. So electric field should point away from positive charges. So that's what away means, yeah. Away may mean to the right. Away, the same word, may mean to the left, depending on our physical location. But we have to imagine that this plate has no edges. It's infinitely large. So exactly same electric field will be measured everywhere. That's it, nothing else. So if we place any charge at any location, it will experience exactly the same force. Now we have to draw a similar picture for a negatively charged plate. Let's place it here. For the moment, we have to forget about anything red on the screen. So the arrows must have exactly the same length. But now they should point how? They should point toward the plate. So toward again means either to the right or to the left, depending on actual physical location. That's the most difficult part, drawing those arrows. Now, we have to calculate the net electric field. And net electric field is the sum. And we can see that for each location, we have to add 2 arrows. Well, we have 3 regions, number 1, number 2, number 3. For each location, we have to add 2 arrows. And the result depends on the region. Let's say number 3. The result is 0. Number 1. The result is 0. What about between the plates? 1 arrow plus 2nd arrow, bless you. The result is not 0 at all. This black arrow now represents the electric field, the net electric field between 2 plates. How should we demonstrate the result? Well, 2 plates, one is positive, one is negative, and there is no electric field outside. There's only electric field inside, and that electric field is uniform and points from positive plate to negative plate. That's the net electric field. And that's it. So we just have to take this expression and multiply by 2 to get the strength. To get the strength of the field between the plates. So why is it convenient? Because this is how we can generate a uniform electric field and then run many different experiments with charges traveling inside it. Because when electric field is not uniform, the force will be different and it's hard to study. But when electric field is uniform, a charge placed in it always experiences the same force, constant force, which will be equal to what? It will be equal to the product. Place a charge Q. It will be equal, no, Q, this type Q is taken, so little q. If we place a charge in this electric field, the magnitude of the force will be equal to the product of magnitude of the charge times the magnitude of the field. That's it. Okay. That's not a question for the web assign, but I will ask you to choose your answer and vote for that. Today is not the best day for any demonstrations, but the air in my room is much drier than the air here, so I keep them in my room, and I hope that something would work today. That's just a hope. So first what I want to do, I want to check if this machine, which has a name, Wimhurst machine, is working today. Because if it doesn't work, that's it. I'm just going to wheel it back. Well, it's squeaking. It's a good sign. Okay, it makes sparks. That's a great sign. Well, actually, what is happening, very simple. There are brushes here which rub against plastic and metal, and rubbing generates charge separation, and some charge now travels and accumulates in one jar, in a second in another jar, and when the charge reaches certain value, the electric field strength here is high enough to make a spark to break the air gap, you know. All right. So if I can generate charges, I can generate electric field between the charges, and if I have a dipole placed in a uniform electric field, well, we always have only two options. Option number one, nothing going to happen. Option number two, something going to happen. If we go with something, next step is what could happen. And if it's a mechanical object, it could move, for example, left or right, up or down. It could spin clockwise or counterclockwise. So if you think nothing going to happen, please raise your hand. Wise choice. Moves to the right. Moves to the left. Rotates clockwise. All right, let's see if that is correct. I don't know. How would I know? I have to think it through. Sorry. Not thinking in physics. I have to draw it through. So here I have a negative charge, which is placed in electric field which points to the right. And because the charge is negative, the force acting on it should point to the left. So that is the force acting on a negative charge. Here I have same electric field, and the charge is positive, which means force acting on this charge should point in the direction of the field. So what we have is something like this. A solid object with two forces acting on it. One force acts like this, second, well, to the left. Second force acts to the right. So we studied this situation before. We know that net force will be equal to 0. But if net force equals 0, it doesn't mean nothing is happening. We also have to check torque. Net torque is not equal to 0. Torque will be actually, how do we call this direction? Counterclockwise. So it should spin, yes, but it should spin counterclockwise. So what does it mean? It means if we take a dipole, place inside the electric field, it starts rotating. And this is how we can see electric field. Maybe. We'll see if we can see. Okay. That works now. So what I have here is so-called grass seed viewer, because what you see here just tiny, tiny grass seeds in oil, in the mineral oil. All right. Now, I can place two parallel electrodes. Well, nothing happening. And now I have to generate electric field between those two plates. To do that, I have to induce a positive charge on one plate, a negative charge on another plate. And that's what this machine is for. We know it worked. Hopefully it still do something. Yes. And now we can see the lines between the plates, because each individual grass seed now takes the orientation of electric field, and we don't see actually anything outside. We see something close to the edges because, of course, these plates not infinitely large. But if we close to the middle point, the electric field is practically uniform. Well, let's see something else. So that's this system has a name, a parallel plate capacitor. We have two parallel plates. Now let's take a look at just a single point charge. Let's hope it still works. Do you? All right, it's getting there slowly but surely, close to the dot. We can see the motion starts. So there are lines. Yeah, it's not very easy today to generate a strong electric field. What else want I try for the future? This one. This is also a type of a capacitor. But instead of parallel plates, we have two cylindrical surfaces. Okay, we can see again that there is electric field between these two plates, but nothing is happening inside, which means there is no electric field inside of this circle. But inside of this circle means outside of the plates. It is consistent with our analysis. There's nothing here as well. So only between the plates we have an electric field. Let's see if sharp point works. Okay, this is a situation called a sharp point. A sharp point is important because, for example, the lightning is a sharp point. We place it into the lightning rod. We place it in the ground. So we can see electric field lines. And we can see that close to the sharp point, we have many, many lines. Density is high. But for example, away from it, we practically don't see anything. So electric field in general, of course, depends on the curvature of the surface. Only for parallel plate, the equation for electric field is very simple. when we have something more complicated, it depends on the bending of that surface. And when sharper the surface is, the stronger electric field is closer to that sharp point. All right, it worked. Which is unusual. Which is good. So, electric field, I just answered this question. Electric field is not a fiction, it exists. And let's see if the next experiment works. You can't answer anything yet, we don't know what you're going to see. One more device. And I want to check again if it works. Otherwise, I will have to fake the experiment. It is based on the same principle of rubbing two materials against each other. In here, we have a plastic belt and plastic from a different plastic, a cylinder. Again, the charge is supposed to be separated and accumulated. Oh, it does work. It makes a good spark. And I always recommend to discharge it first, because if you don't, you can get shocked. A large spark means the, well, you know, voltage thing, yeah, in a power outlet. So large spark means high voltage. Now the experiment. Now the question. Naturally, the electric field was the reason for these peanuts move. It couldn't be done by gravity or anything else. So if electric field did any work, you should choose, well, I don't know, number one. If it didn't do, number two. If you're not sure, something else. These are too expensive to lose. Well, we had to compare two situations, before and after. Let's say a single peanut is resting, initial speed is 0, and then the same peanut is moving, flying away. Speed is not 0 anymore. What does it mean? It means kinetic energy of this peanut changed. And the change in the kinetic energy is equal to what? Net work, total work, net work. But in this situation, that's going to be the work done by electric field. So definitely, yes, electric field does work. Well, if it does work and the energy changes, that means we have to review. And by saying we, I mean you, have to review everything we know about energy and work. So, for example, there is mechanical energy, which is the sum of potential and kinetic. And potential energy, by definition, is something, the difference of which is equal to the work. We use this expression, this definition, for calculating elastic potential energy, but we can use the same definition to calculate any type of potential energy, actually, and for gravitational potential energy. and for electrical potential energy now. Kinetic energy, work kinetic energy theorem, law of conservation of mechanical energy, all that information has to be refreshed. Now, we can use the analogy between gravitational field and electric field. We know now how to generate a uniform electric field. So, of course, we have to start from calculating work done by a uniform electric field. Let's do it. We imagine in a simplest situation possible a single positive charge located in a uniform electric field and nothing else is acting on it. So we actually don't really need to see the plates or field lines. All we need to see is a charge and the electric field acting on it. As we know, electric field results in a force, and if the charge remains constant, it doesn't lose any parts, and electric field remains constant, hence the force remains constant. For the constant force, work done by the force is equal to the product of three variables: the magnitude of the force, the magnitude of the displacement of the object, times the actual value of the cosine of the angle between the force and displacement, PY105. We just know that. Now, if we wait for the charge to move to a new location, that's the initial location, that's the final location, this black arrow will represent the displacement. And what is the angle between the force and displacement in this case? 0, there is no angle. So if you want to calculate work now, we just have to multiply the magnitude of the force, which is Q times E, times, so for now it's just delta S, the magnitude of the displacement. Now what can we do? Well, we can introduce the x-axis. And now we have to introduce a new rule for introducing x-axis. The new rule says it has to point in the direction of electric field. New situation, new rules. So that's going to be x initial, that's going to be x final, and the expression will be equal to the product of a charge times the electric field strength times the difference but what we know that according to a definition of potential energy is such a thing, the difference of which is equal to work. This is a definition of that physical quantity we call potential energy, and this is the actual expression for potential energy for the work. So what we can extract from this? Well, it is equal to negative xi qe minus negative xf qe. Minus and minus made it plus. Why do I need this minus? Because I want a difference. Now we can compare two expressions and make a conclusion. In this specific case, that's a specific case, this is how we can calculate potential energy over charge. And of course, it doesn't matter if it's initial, final, it's just an expression. And we will not actually use this expression well, maybe once in the future. But this is just a good illustration of the strategy. And the result tells us something very important. Potential energy over charge is related to the charge and location of that charge. How? Well, in the easiest case of a uniform electric field, this is how. But we don't always have a uniform electric field to deal with, so we'll have to figure out a different equation in the future. Well, so this is the conclusion. Of course, we can repeat the same calculation for a negative charge. The strategy doesn't change. And of course, we get exactly the same expression. We just have to remember in this expression, Q represents the actual value of a charge. If it's positive, it's positive. If it's negative, it's negative. That's it. And we can see that for electric charges, when they released from rest in electric field, they behave in the same way like a ball released under the force of gravity. On its own, it always moves from a higher potential energy to a lower potential energy. We have to do some work to bring it to a higher potential energy. And when we don't touch it, let it move, it always wants to reach the state with the lower, theoretical lowest possible potential energy. And that also works for charges. If we release a positive charge in the electric field, it will be moving from the current location to a location with a lower potential energy. Same with the negative charge. If we let it go, it will be moving from the initial location to the location of the lower potential energy. So, the summary, we have a charge placed in electric field. It has energy, we call it potential energy. And don't answer this question. A positive charge, Q equals plus 1 coulomb, is placed at a location, point P, where the potential energy is equal to 10 joules. Okay. So here, the potential energy of this charge equals 10 joules. That's what we know. And the question is, if we remove this charge, but instead we place a charge of 7 coulombs, what will be the potential energy of that charge? Well, of course, it's going to be 70. The answer is 70. Now we're done. I'm going to start from this tomorrow. Don't forget, tomorrow is Wednesday. Thank you.